Okay, so Assalamualaikum warahmatullahi wabarakatuh. Okay, now we move on to our next subtopic in the bonding theory, which is the molecular orbital theory. So previously you have learned the VBT, okay, you have learned the CFT, okay. So the VBT, okay, what you have learned is actually you learn how to determine the magnetism. Okay, but however, from this theory, okay, you cannot determine its color and the depth that correspond to the magnetism. Whereas when you learn this theory, you know why all the coordination complexes have variety of colors and they have variety of magnetic properties, okay, such as the para, dia, high spin and low spin. Okay, so when you learn, okay, with these two theory, you always look up for the spectrochemical series. Okay. Okay. However, okay, you cannot understand or prove why those series exist. So that's why, okay, the MOT, okay, comes along lah. So this MOT is actually, okay, to explain, okay, the spectrochemical series. Okay. So as you can see here, each of the theory is actually what we call overcome to the disadvantages of each theories. For example, the CFT, it overcome the variety of magnetism and the color of the complexes, while the MOT, okay, they overcome, okay, the spectrochemical series, because this spectrochemical series cannot be explained using VBT and CFT. Okay, so before we move on into MOT, let us refresh. Actually, MOT you have learned it during your in your organic chemistry. Okay. So the MOT that you've learned in organic chemistry is the molecular orbital theory for organic compound. Okay, so basically it will involve S and p orbital. Okay, so for these coordination complexes, so as we all know, it is a coordination complex, so it must have another orbital, and it must include the d orbital. Okay, so for example, okay, in octahedral complex, okay, octahedral complex. Okay, so when you see a complex, it must be a reaction between metal and ligand. Okay, and how it comes together, or how it becomes a complex, they actually form a dative covalent bond. So remember, this one you have learned during your inorganic classes before. Okay, so dative covalent bond. So why I say dative? Because the two lone pair, okay, from the ligand, okay, donate, okay, its electrons to the empty orbital of the metal. Okay, so it forms a covalent bond, a dative covalent bond. Okay, so this, okay, will be shown, okay, ataupun will be proved, okay, by the MOT. Okay, for example, an octahedral complex. So this is your M, ligand, 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 and ligand. Okay, so you have an octahedral complex. So the orbital for the M here, Okay, so the M will have the orbital as P and D. For example, if you have a 22 atomic number of metal, so the electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d4s2, 3d2. Betul? 6, 8, 10. Okay, 22. So it means that for the metal complex, it consists of S, P, and D. S, P, and D orbital. Okay, so the orbital will be S, P, and D. Okay, so for the S orbital, you only has S lah. While the P orbitals, okay, you can have, okay, for the P orbital, you can have Px, Py, and Pz. While the D orbital, you have Dxy, Dxz, Dyz, dx square minus y square, and dz square. Okay. Okay, and then each of the orbitals will have symmetry symbol. Okay, ingat lagi tak symmetry symbols? Okay, the symmetry symbol. So the symmetry symbol for the S will be A1G. The symmetry symbol for the P will be T1U. The symmetry symbol for the D, okay, it will divide it into two lah for D. Okay, so the first one will be the T2G, and the second one will be the EG. Okay, so do you know what it means by A, T, and E kat sini? Okay, so it has its meaning. Bukan saja dia buat A, T, E, and etc. lah. Okay, so let us refresh again. Okay, the A symmetry symbols, okay, correspond to the non-degenerate orbital. Why I say it is a non-degenerate orbital? Because S only consists of one orbital. Okay, S ni consists of one orbital. So dia tak ada other degeneracies. So that's why we call it non-degenerate orbital, or the L equals to 0. So dia tak ada non-degenerate orbital. While the T, okay, the T here, the symbol T here, okay, why it state T? Because it has triplet ataupun triplet. Okay, triply degenerate. Okay, why I say this? Because the P orbital has 3 degeneracies. 1, 2, and 3. That's why T. Same goes to the T to G, because it has 3 degeneracies. Okay, so that's why it has T. While the E, okay, is corresponds to the doubly degeneracy, or doublet lah. Okay. Okay, why? Because if you look at dx squared and minus y squared and dz squared, it only consists of 2 degeneracies. Okay, let me just refresh lah. Supposedly you have known all the terms. Okay, so back to the MOT. So the reactions, okay, between the metals and the ligand, to make that compound, or to make, for example, an A compound here, okay, to make A compound ataupun A complex, okay, the atomic orbitals, okay, of the to form the complex, okay, the atomic orbital of the metals and the ligand must be symmetric. Okay, so kita akan tengok nanti later on. As I mentioned before, to form a complex, okay, the atomic orbital of metal and the ligand must be symmetric. Okay, what I mean by this, okay, first of all, okay, we look at this structure. It is an octahedral structure. Okay, so for this octahedral structure, the ligand, okay, the ligand will sit, okay, ataupun the ligand is at the dx square minus y square and dz square of the metals. Okay, so the ligand sit, okay, ataupun the ligand fill in the orbitals for the metals, okay, at dx square minus y square and dz square orbital, which is this orbital. For example, here, okay, so m dx square minus y squared orbital and dz squared. Okay, so the ligands for octahedral geometry will fit in these orbitals. Okay. Well, for the ligand, okay, to make an octahedral geometry, and okay, please bear in mind this is a sigma bonding. Okay, so maksudnya if it's a sigma bonding, so the orbital must be overlap. Kan, this similar to what you've learned in your organic class. So the orbital must be overlap. Okay, so tak kisahlah is it an SS or overlap as in p orbital. Saya ingat lah. Okay. Okay, so here your ligand ni, okay, must, okay, your ligand, your choice of ligand can be an s orbital. Okay, why I say an s orbital? Because s can simply fit in here. Okay, so you can make an octahedral geometry, or your ligand is or your ligand has p orbital. Okay, so why p? Because for the p orbitals you have 3 degeneracies, which is the px, py and pz. So each of degeneracies for the p orbital, okay, is at or is along that x and y and z axis. So similar to your octahedral, where your ligands sit along x-axis, y-axis, and z-axis. So it means that you can have, okay, your ligands with p orbital. Okay, faham? So atomic orbitals, okay, as I mentioned before, the atomic orbital of the metal and ligand must be symmetric. Okay, so this is your metal, this is your ligand. Okay, so your atomic orbital for your metals, okay, your metals might have A1G, the T, EIU, T2G, and EG, whereas your ligands can have A1G correspond to the s orbital, okay, or T1U and EG. Okay, so these are the ligand orbital symmetry, and these are the metal orbital symmetry. So why is it this way? Okay, sebab this one is the S, kan? SPD semua ni. Okay, and this one kalau you tengok the geometry of your complex, okay, is at along x-axis. Okay, so sini ada x, y, and z axis, and sini pun ada x, y, and z axis. So samalah. So yang ini ada x, y, and z axis. This one has x, y, and z axis, and this one can have x and y and z axis because it is s orbital ni, satu-satu ni. Okay, so from here, okay, kalau you tengok kat sini, okay, how many orbitals, okay, okay, that can be formed. Okay, for A1G, okay, you can have 1 orbital. For TIU, you can have 3 orbital. For T2G, you can have 3 orbital. For EG, you can have 2 orbital. Remember, okay, the degeneracies. A, you have 1 degeneracies. T, you have triply degenerate. 3, you have triply degenerate. E, you have doubly degenerate. So total altogether will be 3, E, 6, 9 orbital. Okay. So as you can see here, metal has A1G, ligand also have A1G. Metal has TIU, ligand also has TIU. Metal and ligand has EG, while the ligand didn't have T2G. Okay, so that's why for an octahedral geometry, ni octahedral, for an octahedral geometry, the T2G, okay, the T2G here termed as the non-bonding orbital. Okay, faham? Okay, why? Because the ligand doesn't have the T2G orbital. Okay, so for nak tengok mana lagi? Okay, so to make a sigma bond for an octahedral geometry, okay, it consists of 6 orbital. Kenapa 6? Okay, so initially we have 9 orbital, okay, but only 6 orbital are the same. Okay, another 2 ataupun another 3 orbital is the non-bonding orbital. Okay, so this is applied for sigma bond for an octahedral geometry. Okay, now we look at how to draw the MOT diagram. Okay, the MOT diagram for an octahedral complex. Okay, for octahedral complex. Okay, this one is for the sigma overlapping or sigma bond. Okay. So to build or to draw the MOT diagram, of course, we must have two sides. Okay, so the first on the left hand side will be the metal. Okay, so the metal, okay, as I mentioned before, so it will have several degeneracies or several symmetry symbol. Okay, for example, we have D, and then we have the, okay, this one n minus 1D. Okay, and then you have the NS and NP. So for the ND, you will have the T2G and EG done. The NS you will have A1G, while the NP you will have T1U. Okay, so this is on the metal side. And then the other side will be your ligand. So this is your ligand. Okay, so your ligands, okay, usually will have A1G, okay, T1U and T2G and the EG kan dx square minus y square and dz square tu. Okay, so your ligands, as it is an octahedral complex, so your ligand must have 6 compound lah, ataupun we will have 6 ligand. So each of the ligand will correspond to 2 electrons. So when you have 6 ligand, so the total electrons for the ligands will be 12 electrons. Okay, so here you will have 12 electrons. Okay, so how do you draw the molecular orbital theory? So the lowest energy will be the A1G. So you will have A1G comes from the ligands, and also have A1G that comes from the metal. Okay, the next one will be T1U. Okay, so it is at higher level from A1G. So same, it will comes from the ligand and as well as the metal. Okay, and then you will have the EG orbital, okay, from the ligand as well as from the metal. Okay, so these energy level, these 3 energy levels. Okay, so these 3 energy level will fit, okay, their electrons from the ligand first. So the ligands will fit in all the 6 orbitals in this energy level. Okay, can for example here lah, kalau EG you have 2 degeneracies, T1U you have 3 degeneracies, A you have 1 degeneracies. Okay, and then you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so here on this lower energy level, or we can say that below, okay, the ligand level, okay, so these all, okay, will occupy by the electrons from the ligand. And then, okay, and then you will have the star block. Okay, so you will have T1U star. So this one corresponds from the metal as well as the ligand. And then you will have A1G star, okay, from the metal and as well as from the ligand. Okay, and then you will have the EG star from the metals and ligand. So as you can see here, okay, each of the orbital here, A1G, T1, T1U, EG. Okay, so these are the bonding orbital. Okay, we'll have the star bonding, which correspond to the anti-bonding. So each of the bonding orbital, okay, will be paired with their anti-bonding orbital. Okay, dia akan sama-sama ada. So bila ada A1G, so this is A1G and anti-bonding orbital. EG, okay, with the EG anti-bonding ataupun EG star anti-bonding orbital. Okay, whereas there will have one more orbital, okay, which is here, same level as the metal. Okay, so it will be the T2G. The energy level will be the same energy level as the metal. So why, okay, it is drawn like that? Because this one, okay, we say that it is free ion. Okay, why we say that? Because it didn't participate in the sigma overlapping, participate in the sigma overlapping or sigma bond. So this T2G correspond to the non-bonding orbital. So bila dia non-bonding, okay, they won't have any anti-bonding lah, sebab dia tak ada bonding pun. So it is a non-bonding orbital. Okay, so let's look at the examples later. Okay, for example, you have this cobalt complex. So first of all, when you want to solve any metal complexes, the first thing that you need to do is find its metal oxidation state. So the metal oxidation state here for the cobalt is okay, carilah. Okay, so cobalt has 27 atomic number. So when you write your electronic configuration, so you will get 3D, ini write betul lah electronic configuration, then 1s2, 2s2, blah 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 ni. Then you will get 4s2, 3D, 7. Okay, and then you have to find the oxidation number of the cobalt. So it has NH3, or ammonia is its ligand. So the charge for ammonia is 0. So the M oxidation state will be 0 times 6 will be plus 3. So it means that cobalt is 3 plus. So when it's 3 plus, so you have to minus out your atomic number with 3. Then you get 24. So based on your electronic configurations, to have a 24 electrons, okay, so you have to minus out 3, then you will get 3d6. So it means that the CO3 plus is d6. Okay, so that is the first thing you need to do lah. And the second thing, okay, you look at the ligand. So this ligand is NH3. So NH3 ligand, okay, as you know, it is a strong field ligand, and it can arrange its electrons, okay, from the metal side lah. Dalam metal punya degeneracy, it arrange as low spin arrangement, because as you see here, the metals group in D6. So D6 will have two types of arrangement, which is the low spin and high spin. So how do you arrange electron in your d orbitals? Okay, so you have to look at your ligands. So your ligand is ammonia, so ammonia is strong field ligand, so you arrange your d electrons as low spin arrangement. Okay. And then your ammonia here has 6 ammonia or 6 molecule. Okay, so it means that it will have 12 electrons. Okay, so one ligand will contribute 2 electrons. So if you have 6 ligand, so it means that it will have 12 electrons. Okay, then we start. Okay, let's start to draw the molecular orbital theory. And remember, this is a sigma overlapping. Okay, kita belum masuk lagi pi overlapping. So this is a sigma overlapping. Okay, so this is a metal side. Okay, so you have 1, 2, 3, 4, 5 degeneracies for the metal or for the cobalt. So it is a cobalt 3 plus or it is a D6. So it consists of 6 electrons. 5, 6. Okay, and then on this side, okay, so you have your metal, your ligand, which is your ammonia. So your ammonia is 1, 2, 3, 4, 5, 6. You have 6 ammonia. Okay, so this is your ammonia. 6 ammonia. Each of the degeneracies consists of 2 electrons. 4, 6, 8, 10, 12 electrons. Okay, sama lah, 12 electrons. And then you fill in the energy level. So the lowest energy will be the A1G. Okay, and then the higher energy will T1U, and then your EG, and all these electrons, okay, correspond to your ligand. So total will be 12 electrons. Okay, so sama lah. Okay, and then you have another 6, okay, coming from the metals. So where does it fit? So it is an octahedral, and this is a sigma overlapping. So bear in mind you have one non-bonding orbital, which is the T2G. Okay, so you have the non-bonding orbital. Lepas tu barulah you ada the EG. Then you will have the EG star or the EG anti-bonding orbital. Okay, and then you will have the A1G star, A1G anti-bonding orbital, and finally the T1U star. Okay, which is the anti-bonding orbital. Okay, so you have 6 electrons to occupy lagi. So you have to occupy at the T2G because yang ni lower. So you occupy another 6. So how do you arrange your electrons? Okay, so since it is a low spin, so you arrange them at this low energy. Okay, bukan bawa naik atas. Okay, and then this gap here, okay, is your delta O. Okay, so if you write up your energy filling, your energy fill up ni, energy but electrons ni will be tak nampak, will be A1G consists of 2 electrons, T1U 6 electrons. EG, you have 4 electrons. T2G with 6 electrons. Okay. Let's look at the other examples. We have this complex, okay, still a cobalt complex, but with fluoride ligand. Okay, so as I mentioned before, the first thing you need to do is to find what is the oxidation state of the metal. So M, okay, plus the ligand charge is -1 times 6 equals to -3. So your metal or your cobalt will have oxidation state of 3 plus. So cobalt has 27 atomic number. So when it's a 3 plus, so it will have 24 electrons. Okay, so similar to the previous example. So your cobalt will be in D6. Okay, so it groups as D6 because it's a cobalt 3. Okay, so the difference between the previous example and this example, the fluorine or the fluoride ligand. So the F is a weak field ligand. So when it's a weak field ligand, so you have to arrange your electrons, okay, at the d orbitals too, as high spin arrangement. So but remember, it has d6, or it groups, and in the d6 d6 metal, so it might have two types of arrangement: low spin and high spin. So in this case, it arranges high spin arrangement. Okay, so similarly, okay, you have to draw your molecular orbital theory. So you have metals here, 1 2 3 4 5 metals here. You have 6 electrons for the metal, okay, and you have your ligands here. So you have 6 ligands, 1 2 3 4 5 6. So you have 12 electrons. Okay, so this is your 6F minus. Okay, and then you arrange the electrons, okay, ataupun yang ligands electrons in here, A1G, okay, T1U, and then your EG. So 1 2 3 4 5 6 7 8 9 10 11 12. Okay, and then it must have the anti-bonding. So you have the EG star, A1G star, and T1U star, the anti-bonding. Okay. Okay. Ni buatlah. Ini. Okay. Okay, and then as this is a sigma overlapping or sigma bond, so you have one level here yang same as the metal energy level, and this one is the T2G, or this is the non-bonding orbital. Kan, this is a non-bonding orbital. Okay, this one only present in a sigma overlapping, okay, or sigma bond. Okay, so they have 6 orbitals for the metal, yang tu je yang belum susun lagi, and since it is a weak field ligand, so you have to arrange as a high spin. So you have to arrange 1 2 3 4 5 6. Okay, so maksudnya the electrons, so you fill up until the EG star. So your delta O will have a smaller delta O lah, rather than your previous samples ataupun your previous complex. And then, okay, how you write up your electrons, fill up ni ataupun electronic configuration, it will be A1G2, T1U6, EG4, T2G24, and then the EG2, 6, 12, 4, 5, 6, 7, 8, 18. Okay, so altogether will be 18 electrons. Okay, now we look at the pi overlapping of pi bond. So previously with the sigma, the orbital is overlapped along the axis. With the pi bond or pi overlapping, the overlapping is on the sideways. Okay, so as an octahedral geometry complex, okay, the sideway overlapping, okay, can occur in T to G orbital, where dxy, dxz, and dyz orbitals are in between the axis. And in between the axis, so that's why the T to G can form or can have the pi overlapping. So this pi overlapping for the complexes, okay, have two types. The first one is the pi donor ligand. So the pi donor ligands, okay, the examples of the ligands for the pi donor ligands will be the fluoride ions, okay, chloride, bromide, iodide, H2O, and OH, hydroxide. While the pi acceptor ligand, okay, the example or the choice of the ligands will be the CO, CN, NO, bipyridine, okay, or biphenyl, and etc. So this is the MOT diagram for the pi overlapping. So previously, okay, you have you have learned the sigma overlapping, where you have this energy level, or this is a T2G energy level. So this T2G energy level is as same energy level as your metal energy. Okay, why is that? Because of this T2G is a non-bonding orbital. Okay, why we say it is a non-bonding orbital? Because this T2G in a sigma overlapping ataupun sigma bond, okay, this T2G didn't participate in the bonding. Okay, while for this pi bonding ataupun for the pi overlapping, okay, you have the participation of the T2G orbital. Sebab apa? Ingat, the pi bonding is the overlapping of the orbitals is at this sideways. So the T2G orbitals are in between all the axes. So that's why the T2G, okay, can participate in the orbitals. Okay, so that's why we cannot, we no longer see this T2G here. Okay, so dah tak adalah non-bonding T2G. Okay, so this is an example for the pi acceptor. So what's the meaning of the pi acceptor? Okay, so what's the meaning of the pi acceptor? So pi acceptor in definition, okay, in definition, the pi acceptor is interaction between d pi with pi star. What it means by this? It means that the d pi from the metal, okay, from the metal, yang sini, from the metal will interact, okay, with the pi star, okay, with the pi star of the ligand. So this pi star is actually MT pi star. Okay, faham? So that's why you won't see any electrons here lah. So it is a pi star ligand, or we term it as ND0 because it is an empty pi star of the ligand. So the pi star and the sigma ligand will have a difference in energy. So the sigma ligands will have 6 orbitals, while the empty pi star ligand will have 3 orbital. Why 3 orbital? Because it is T2G. Okay, so there are 3 orbitals. Okay. Okay, now let's look at the pi acceptor arrangement. Okay, so as I mentioned before, you no longer have this non-bonding orbital. So because of the participation of the T2G, so when the T2G participate, or when you have a bonding of T2G, then you must have the anti-bonding of T2G. Okay, alright. So here this is similar to the sigma bond. So here the electrons will occupy from the sigma electrons from the ligand. So let's say you have 6 ligands, so you will have 12 electrons. So all 12 electrons will occupy here lah. Okay, and then as you can see here, the T2G energy level is slightly below the metal orbital, or the metal energy. Okay, so that's why you can say that this T2G orbital will have more characteristic of the metal. Okay, and then this T star, T2G star, okay, will have more characteristic of the ligand. That's why when you calculate the delta O, okay, when you calculate the delta O, it will be the difference between this energy, the T2G and the EG star. Okay, alright, because the T2G will have the characteristic of the metal same as the EG. The delta O must be kita boleh kata comes from the d orbital lah, ataupun the metal orbital. So the distance between the energy distance to calculate the delta O must be between the T2G and EG star. Okay, not the EG between the T2G, the EG star and T2G star. Why? Because the T2G star has more characteristic of the ligands, bukan metal. So as you see here, the delta O will be in a larger value. Now we look at the molecular orbital theory with the pi donor ligand. So by definition, pi donor ligand, okay, is the interactions between the d pi and d pi. So the first d pi, okay, is the metal, and this one comes from the ligand. Okay, so it means it is in contrast with the pi acceptor ligand. And then another difference, okay, between those characteristics, okay, from pi acceptor and pi donor, you look at the ligand here. So the orbitals for the sigma ligand and the pi ligands are on the same energy level, sama. Okay, whereas if you flip back your notes with the pi acceptor ligand, the sigma, the energy level, you have two different energy levels between the sigma ligands and pi acceptor ligand. Okay, so in this case, okay, all the orbitals for sigma and the pi ligands will be at the same energy. Okay, so look at here. So you will have 1, 2, 3, 4, 5, and then you have another missing orbital actually, none. Okay, so take notes. You have another one, which is 6. Yeah, so these 6 orbitals okay, correspond to the sigma ligand. Okay, and then you have another 3 correspond to the pi ligands. So why 3? Because the pi, okay, have T2G punya characteristics, okay, based on the octahedral geometry. Okay, the next thing, okay, the difference between the pi acceptor and pi donor lagi. Okay, you look at the energy level here. So this T2G energy level, okay, is just below the ligand's energy level. So that's why this T2G, okay, this T2G will have more characteristic of the ligand. Okay, senang nak kata, this T2G, electrons in T2G will come from the ligand. Okay, whereas the metals electrons, okay, will fill up in the T2G star and EG star. Okay, because remember, this is a pi overlapping, so you won't have any T2G here. The T2G no longer non-bonding. The T2G will have bond. Okay, so for the metals electrons, okay, it will fit on the T2G star or T2G anti-bonding and EG anti-bonding. Okay, and then what about the delta O? So the delta O you will calculate between the T2G and EG star, T2G star and EG star, between this, because these orbitals occupy the electrons from the metal, the D metal. Okay. So in summary, so based on the spectrochemical series, so starting with iodide, which is the weak field ligand, okay, and this carbonyl, which is the strong field ligand. Okay, so this iodide is actually a strong pi donor. Okay, it's a strong pi donor. So that's why, okay, it has small delta O. Okay, So how do you prove this? You prove this using the pi donor ligand MOT, the molecular orbital theory of the pi donor ligands. Then you can see the delta O is smaller. Okay. And then across this series, okay, so you can have a strong donor at strong pi donor, and you can have a these two is a weak pi donor. Okay, so when you have a weak pi donor, so the delta O might increase a little bit, increase sikit sahaja, but not too much. Okay. Well, for these two compound, okay, is we can say a neutral, where you can okay, where you won't see any pi effect, any tak ada pi effect. Okay. And then when we move on to the ethylene diamine, okay, so it start to have a characteristic of weaker pi acceptor. So the delta O, okay, it tends to increase. And then at the end of this series, where you have a strong field ligands, where it is a strong pi acceptor, where you can have a very large delta O. Okay, sebab ingat bila strong pi acceptor, you have the non-bonding pi. Okay, kan ingat tak, ligand will have the non-bonding pi. So your metal orbital, your T2G, or the characteristic of the metals, okay, the T2G here will belongs to the metals, bukan ligand. And then you have the Eg star. So the delta value will be higher. While for the pi donor, okay, you have a similar energy level for the sigma and the pi ligand, and your T2G here, okay, will belongs or will have the characteristic of the ligands. Okay, this is your metal energy level. So your metal energy will have the T2G star and Eg star. So the difference between these two energy level is lower. Okay, so that's why with the weak field ligand, you have small or lower delta O, because you have a strong pi donor. Okay, so it means that this MOT is actually can have a better understanding, okay, regarding your delta O or your spectroelectrochemical series. Okay, while this one, the CH3 and H is not a strong pi acceptor, this is a strong sigma donor. Dia still buah ni lah. Okay, so ingat yang ini tak ada pun characteristic of pi, but it has strong sigma donor.